Welcome to WikiPodcast. Welcome, listener, to another deep dive. We're continuing our physics series, focusing on the foundations of classical physics. And today, well, we're tackling a big one, force, mass, and acceleration. Really getting into FMA.
That's right. It's probably the most famous equation in physics, or close to it.
It feels like the bedrock idea. So we're going to unpack FMA, figure out what the pieces really mean, and, why it's just so fundamental.
Absolutely. And our sources for this deep dive really walk us through Newton's laws of motion. These weren't just abstract thoughts. They gave us the mathematical tools, the framework that classical physics and, well, a lot of engineering relies on.
Right. So our mission today is pretty clear, but it goes deep. Let's dissect this core relationship. What is force, really? What's mass? What's acceleration in this context? How do they link up in FMA?
And why does it work so well? Why is it such a powerful way to understand how things move?
Exactly. Where do we start?
Well, before we get into why things move, maybe we should establish how we even describe motion itself.
Okay, that makes sense. Like, setting the scene, we see stuff moving all the time, cars, balls, whatever. How does physics actually pin that down mathematically?
So the language for that is called kinematics. And it really boils down to three key ideas.
Yeah.
Position, velocity, and acceleration.
Okay. Position seems straightforward, just where something is.
Pretty much.
Yeah.
Like coordinates on a map. But velocity.
Yeah.
Velocity is about how quickly that position is changing and in what direction. Think of it as the rate of change of position, conceptually like a first derivative.
So it's not just speed, like 60 miles per hour isn't enough. It has to be 60 miles per hour north or something.
Precisely. Velocity is what we call a vector quantity. It has both magnitude, the speed, and direction.
Got it. And acceleration.
Acceleration is how the velocity is changing over time.
Yeah.
So if you speed up, slow down, or even just change direction,
Mm-hmm.
you're accelerating.
Oh, right. Changing direction counts too.
Absolutely.
Yeah.
Because the velocity vector is changing. Think of acceleration as the rate of change of velocity, a second derivative conceptually.
And you said velocity is a vector. Position and acceleration too.
Yes, they are. And this vector nature is, well, it's crucial for understanding FMA. Position, velocity, acceleration, they all have magnitude and direction. So when we start talking about forces causing changes, the direction of that force is tied directly to the direction of the acceleration. That all has to line up.
Okay, so acceleration describes the change in motion. Now let's bring in the things that cause that change. Force and mass. What's the physics definition of force?
In physics, force is basically the way we quantify a push or a pull. Simple idea, but we make it precise. And just like acceleration, force is a vector. The direction you push or pull in matters a lot.
And forces in the real world are things like...
Oh, all sorts. The tension in a rope, friction rubbing against something, gravity pulling things down, the force your muscles exert when you lift something. It's everywhere.
Okay. And mass, is that just the same as weight? Like how heavy something feels?
Good question. Everyday language is a bit fuzzy there. In physics, mass is specifically the amount of matter in an object. It's fundamental to the object itself.
So it's like how much stuff is there?
Exactly. And it's a measure of the object's inertia, its resistance to being accelerated. It's just a number, a scalar. Weight, though, that's different. Weight is the force of gravity acting on that mass.
Okay. So mass is the stuff, weight is the gravitational pull on the stuff?
You got it. They're related. Obviously, more mass means more weight, usually, but they aren't the same thing. Keeping that distinction clear is really important when we get to FMA.
All right. Pieces are on the table. Force, vector push-pull, mass, scalar stuff, inertia, acceleration, vector change in velocity. Let's connect them. Newton's second law, what was his original idea?
Well, Newton's phrasing was actually quite elegant. He talked about the change of motion. What he meant was momentum being proportional to the force applied and happening in the direction of that force.
Momentum. That's mass times velocity, right?
Yes, exactly. So the law, fundamentally, is about how force changes momentum. In modern math, we write that as F equals dB dt. P is momentum, and dP dt is its rate of change over time.
Okay, F equals the rate of change of momentum. How do we get to F?
Well, think about most everyday situations. When you push a box, its mass doesn't usually change, right?
Right, stays the same box.
So if the mass n is constant, we can simplify. Since momentum p is m times v, velocity, the rate of change, dp dt, becomes m times the rate of change of velocity, dv dt.
And dv dt, that's acceleration, A.
Bingo. So for constant mass, f dp dt simplifies down to the famous f.
Okay.
But it's crucial to remember, this is a vector equation. The net force vector, The sum of all forces acting on the object equals the mass times the acceleration vector. They point in the same direction.
Net force. So if there are multiple pushes and pulls, you have to add them up first.
Yes, and you have to add them as vectors, considering their directions. You can't just add the numbers. The combined effect, the net force, is what determines the acceleration according to EFMA.
So is EFMA just like a definition of force? We just say force is whatever makes mass accelerate.
That's a subtle point, and people do discuss it. But it's generally seen as more than just a definition. Yes, it links force and acceleration, but it also quantifies how they're linked through mass. It tells us the same push, force, will cause less acceleration on a more massive object.
Because it has more inertia.
Exactly. And crucially, we can often measure forces independently, like with the spring scale, without necessarily measuring the acceleration they cause. So it's a relationship, a law, that lets us predict things, especially when we combine it with specific rules for how forces like gravity or friction behave.
And that combination, that's what drove classical physics forward for so long. Find the forces, know the mass, use EFMA, predict the motion.
That was the program, pretty much.
Yeah.
Identify all the forces, understand the properties of matter like mass,
Yeah.
and EFMA becomes your prediction engine. It's incredibly powerful.
Let's see it work then. Can we look at some examples?
Great idea. How about starting with something simple, like uniformly accelerated motion?
Okay, what's an example of that?
The classic one is free fall near the Earth. If we ignore air resistance for a moment.
Like dropping an apple, Newton style.
Exactly. Or a bowling ball. When something's in free fall, the main force acting on it is gravity, pulling it straight down. According to EFMA, this constant downward force should cause a constant downward acceleration. We call that acceleration g.
Right, about 9.8 meters per second squared.
Yep. But here's where combining EFA with the law of gravity gets really interesting. You might think intuitively that since gravity pulls harder on heavier objects, they should fall faster.
Right, yeah, that seems logical. More pull, more speed.
Seems logical. But let's use the physics. The force of gravity on an object of mass m near the Earth, mass m, is given by Newton's law of gravitation. F gravity equals gmmr squared. G is a constant, r is the distance.
Okay.
Now set that force equal to ma, according to the second law. So gmmrs equals ma.
Oh, the little m, the object's mass. It's on both sides.
Exactly. It cancels out. So the acceleration A just equals gmr squared. Near the Earth's surface, g, m, and r are basically constant. So A, which is g, is constant. And crucially, it's the same for all objects, no matter their mass.
So the feather and the bowling ball do fall at the same rate in a vacuum?
They do. The bigger gravitational force on the bowling ball is perfectly balanced by its greater inertia, its greater resistance to acceleration. Both effects depend on mass m, so it cancels.
Yeah.
It's a beautiful consequence of how EFMA and gravity work together.
That clears up a lot. So in free fall, velocity increases steadily, distance covered increases faster and faster. What about throwing something like projectile motion?
Right, like tossing a ball. That's essentially free fall, but with an initial sideways or upward push. If we again ignore air resistance, the only force acting on it once it leaves your hand is gravity, straight down.
So the only acceleration is g, downwards.
Correct. EFA says a downward force gives a downward acceleration. There's no horizontal force acting on it, ideally, so there's no horizontal acceleration.
Meaning the horizontal part of its velocity just stays the same?
Exactly. It sails sideways at a constant speed while simultaneously falling downwards faster and faster due to gravity. Put those two motions together, constant horizontal speed, accelerating vertical speed, and you get that characteristic curved path, a parabola.
Okay. What about the very top of the arc? When the ball stops going up for just an instant, is the acceleration zero there?
Ah, common confusion point. No, the acceleration is still g, downwards. Even though its vertical velocity is zero for that split second at the peak, gravity hasn't stopped pulling on it.
Right, the force is still there.
The force is still there, so the acceleration is still there. Remember, acceleration is the rate of change of velocity. At the peak, the velocity is changing direction from up to down, and that change requires downward acceleration.
And this connects to Newton's cannonball idea, orbiting.
It does. He imagined firing a cannonball faster and faster from a tall mountain. Eventually, it's moving sideways so fast that as it falls due to gravity, the Earth's surface curves away underneath it at the same rate.
So it just keeps falling,
Yeah,
but never hits the ground.
exactly. That's what orbit is. It's a form of continuous free fall, constantly accelerating towards the Earth due to gravity, following EFMA. But its sideways velocity keeps it missing. Same principle explains the moon orbiting Earth.
Amazing. Emma covers falling apples, flying baseballs, orbiting moons. What else? What about moving in circles?
Good one. Uniform circular motion. Imagine swinging a ball on a string around your head at a constant speed.
Okay. Speed is constant, so no acceleration.
But the velocity isn't constant. Remember, velocity includes direction. As the ball swings around, its direction is constantly changing.
Oh, right. Velocity is changing, so there must be acceleration.
There must be. And if there's acceleration, ESMA tells us there must be a net force causing it. For an object moving in a circle of radius r at speed v, the math shows the acceleration points towards the center of the circle, and its size is v.
Towards the center.
Yes, and so the force required must also point towards the center, with a magnitude F equals m times that acceleration, so F equals mv/ar. We call this the centripetal force, meaning center seeking.
And what provides that force? The string.
In that example, yes, the tension in the string pulls the ball inwards. For a car turning a corner, it's the friction between the tires and the road. For the moon orbiting Earth,
It's gravity.
exactly. Earth's gravity provides the centripetal force, keeping the moon in its orbit. And this is powerful if we measure the moon's orbital speed and distance. We can use F equals mvr, combined with the law of gravity, FG_meAO, to actually calculate the mass of the Earth. EFA lets us weigh planets.
Incredible. So EFA isn't just straight lines, it's curves and orbits too. What about things that wobble back and forth, like springs or pendulums?
Right, that leads us to simple harmonic motion. This happens when you have a force that always tries to pull an object back to some stable resting point, its equilibrium. And importantly, the strength of that pull is proportional to how far the object is from that equilibrium point.
Like stretching a spring. The further you stretch it, the harder it pulls back.
Precisely. That's described by Hooke's law, F a real max K.
Yeah.
K is the spring constant. X is how far you stretched or compressed it from rest. And that minus sign is key. It means the force is always opposite the displacement, always directed back towards the center.
So if you pull it out, the force pulls in. If you push it in, the force pushes out.
Exactly. Now put that force into ESMA. You get mad as mech x. Since acceleration a is the rate of change of position x, the second derivative, dx dtx, the equation becomes mdx dt is mech dx.
Okay, that looks more complicated.
It's a type of equation called a differential equation.
Yeah.
But the important thing is that the solutions to this equation describe exactly that back and forth oscillating motion we see in springs. And it turns out it's also a great approximation for pendulums swinging through small angles and many, many other systems vibrating around a stable point. ESMA translates that specific restoring force into predictable oscillations.
We touched on rockets earlier, where the mass changes as they burn fuel. How does FMEG handle that? Does it break down?
Not exactly, but we have to be more careful. That's where it's better to go back to Newton's original formulation in terms of momentum. F equals the rate of change of momentum.
Force equals the rate of change of momentum?
Right. Since momentum P equals emv, if both mass m and velocity v are changing, like in a rocket ejecting mass, you have to account for the change in both using calculus. EFA is the simplified version that works beautifully when mass is constant, which is very often the case, but the momentum form is the most fundamental.
Okay, so EFMA is this incredibly powerful, versatile rule. It explains falling, orbiting, oscillations. How does it fit with Newton's other laws? There were three, right?
Yes, 3 laws form the foundation. We've spent all this time on the second law, EFMA. Let's quickly look at the first and third.
The first law, inertia.
That's the one. It basically says an object stays put or keeps moving at a constant speed in a straight line, unless some net force acts on it.
That sounds a lot like what EFMA tells us if the force is zero.
Exactly. It's completely consistent. If the net force F in EFMA is 0, then the acceleration A must be 0. And 0 acceleration means constant velocity, which includes staying at rest, 0 velocity. So you can see the first law as a kind of special case of the second law, really highlighting this inherent property of matter called inertia, its tendency to resist changes in motion. It also sets up the idea of inertial reference frames, where these laws hold true.
Okay, consistent. What about the third law? Action, reaction, equal and opposite.
Right. The third law, for every action there is an equal and opposite reaction. More formally, if object A pushes on object B with some force, then object B simultaneously pushes back on object A with a force of the same magnitude but in the opposite direction.
Okay.
The absolutely critical point here, the one that trips people up all the time, is that these two forces, the action and the reaction, always act on different objects.
So they don't cancel each other out on the same object.
Precisely. Think about a book sitting on a table. Gravity pulls the book down. That's a force on the book by the earth. The table pushes the book up. That's a force on the book by the table. Those two forces do cancel out if the book isn't accelerating, but they're not an action-reaction pair according to the third law.
Okay, so what are the pairs?
The reaction to Earth pulling the book down is the book pulling the Earth up with an equal force. The reaction to the table pushing the book up is the book pushing the table down. See? Each pair acts on two different things.
Right, so that makes sense. Book on earth, earth on book, table on book, book on table. Got it.
And this third law isn't just some quirky rule, it's connected to something even deeper.
Which is?
Conservation of momentum. If you have an isolated system, just two objects interacting, the forces they exert on each other are equal and opposite. Third law. Since FDPDT, second law, the rates at which their individual momenta change are equal and opposite.
Meaning the total change in momentum is zero.
Exactly. The total momentum of the isolated system stays constant. The third law ensures momentum is conserved in interactions. In some really advanced physics, like electromagnetism, the simple statement of the third law needs tweaking. But the underlying principle of momentum conservation still holds, even if momentum gets stored in fields.
Wow. Okay, so let's recap. EFMA is the core rule linking force and acceleration. It relies on the idea of inertia, first law, and is linked to action-reaction, third law, which itself points to momentum conservation. It seems clear why it's central to classical mechanics.
Yeah, it really is the engine. You combine EFMA with specific force laws like gravity or friction or spring forces, and suddenly you can make quantitative predictions about how things will move. It gave physics this incredibly successful program: find the forces, measure the masses, apply EFMA, predict the future. It was revolutionary.
But it's not the final word in physics, right? It has limits.
Oh, absolutely. EVA is the heart of classical mechanics. It works incredibly well for everyday objects, planets, cars, baseballs, basically things that aren't moving near the speed of light, aren't dealing with intense gravity like near black holes, and aren't at the atomic or subatomic scale.
To those you need
Relativity for high speeds and strong gravity, and quantum mechanics for the very small. And even within classical mechanics, there are other ways to formulate the laws, like using Lagrangian or Hamiltonian mechanics, which focus more on energy. Sometimes those are more powerful, but they ultimately reproduce Newton's laws in the right context. EFMA remains the most direct, intuitive link between force and change in motion. It even gets adapted in statistical physics to describe things like Brownian motion, the random jiggling of particles.
So bringing this all back home for someone listening, why does understanding EFMA matter in your life? How does it help?
Now, it gives you a lens, a mental model, for making sense of the physical world all around you. You start to see why things happen the way they do. Like, why does it take more effort, more force to get a heavy grocery cart moving compared to an empty one? EFMA tells you. More mass needs more force for the same acceleration. Why do you feel thrown back in your seat when a car accelerates hard? That's your body's inertia, its resistance to changing velocity described by EFA. Why does a ball thrown up follow that arc and come back down? Gravity provides a constant downward force, causing a constant downward acceleration via EFMA.
So it's the basic grammar for describing motion.
Exactly. It provides the language and the logic to understand and predict how most things you interact with daily will move. And, it's a starting point for so much of the engineering and science that shapes our technology and environment. It's fundamental.
And as a final thought, our sources mention something interesting. Even though these laws seem deterministic, like EFMA gives you a precise outcome, when you apply them to complex systems with many interacting parts, things can get unpredictable.
That's right. The idea of chaos theory actually emerges from applying Newton's laws to systems like, say, 3 planets orbiting each other. The equations themselves allow for situations where a tiny, tiny change in the starting position or velocity can lead to completely different outcomes down the road.
So even simple rules can lead to complex, almost unpredictable behavior.
It's a fascinating aspect. It shows that exploring these foundations reveals layers upon layers, from a basic push to the clockwork of the solar system, mostly, to the possibility of chaos, all stemming from these core principles like EFMA.
Thanks for listening. Write us your opinion on what everyday phenomenon does understanding EFMA help you see differently now. Let us know in the comments.
And please subscribe to the channel to help more listeners reach our deep dives. Thank you and have an amazing day.